Welcome back, everyone. This is the first segment for section 6.2. Now, what we're going to do in 6.2 is we're going to expand on the solutions techniques that we looked at in section 6.1, where we'll start to bring in, at the very least, some algebraic kinds of ways to get to solutions. I don't think that we've moved into anything yet where we use, I don't know if we'll be using anything with identities necessarily in this section, but let me just kind of do this. First thing, rather than dive right into the material as presented in the textbook, what I'd like to do is I would like to kind of give you sort of an overview of what's going on here. So section 6.2. So when you're looking at an algebraic equation, there's several different kinds that we have at our disposal. We have things like what so-called linear equations, and these are I can give you an example of one where, say, I don't know, 3x plus 2 equals 7, right? And you know how to solve a problem like that, and you've done it for years. We have so-called, well, let me do them kind of in the order, equations that are of higher order that possibly can be factored in some way. So like we may call this just simple or just factoring methods. And this would be a situation where you have something like, let's see, like x squared plus 4x plus 3 equal to 0. And as you know, one of the ways to approach a quadratic, the first thing to do is to try to factor it. But this kind of is maybe a little more simplistic than what we're after here. Because we may have mixed trig functions, for example. And so maybe if you saw something that looked like x squared plus x times y equal to 0, this might be more characteristic of kind of the stuff that we're seeing in this first section on trigonometric equations, where you would simply factor out the x, and then you have one solution where x is equal to 0, and then you have another solution where x is equal to negative y. So those can sometimes come up as well. It's often, you don't usually get this lucky though. There's also, in this kind of case happens as well. And what I'm trying to make a comparison to is the variables that I'm writing here, instead of just being x or y, these are actually trig functions as well. So we're expanding on what we already have. And then finally, you have for sort of standard sorts of algebraic problems, you have, and all we're going to focus on in this section is going to be what are called things that quadratic methods that don't involve simple factoring. Now, in this case, you might have maybe a quadratic equation that is not easy to factor, or even possible to factor with whole numbers. Something like, say, x squared plus 2x plus 5. I don't think that could be factored. Let me just think a second. So that'd be 4 minus. Yeah, this might have imaginary roots. Maybe not a great example, but anyways, it's easy enough to find what the solutions to this equation are, because we have this thing called the quadratic equation, right? And so if we plug that into that formula, we'd get x is equal to negative 2 plus or minus the square root of 2 squared minus 4 times 1 times 5. All over 2 times 1. And like I said, I think you're going to get an imaginary root here. But anyways, this is the method. So this is kind of the big picture of what we're trying to do in terms of finding solutions to equations that are more complicated than ones we had before. Because what we've looked at so far is any equation where you have some trig function of some angle is equal to some number, right? This is far more simple than just even linear equations, right? Because here you've got it down to its equivalent. This is kind of, once you've done all the solution methods up here, any one of these, then this is kind of the finished result. So with trigonometric equations, what we're basically trying to do is we're trying to use algebra to boil these things down to a series of equations that look just like this. And then depending on which trig function it is, you find both the principal root and then the alternate root. And we still haven't really said anything about, I think I'm going to work a couple here. Since this is where this is first introduced, I think, if I'm not mistaken, I think this section, maybe they don't do any yeah, there's a couple where they find all real solutions. So the next sort of task that we need to be cognizant of is beyond just the principal and the alternate root, we also need to add in the period. So this might be a good time to kind of discuss that idea. And I think I'll just start on a fresh sheet. So recall, if you end up with a situation, page 2, if you end up with a situation where you've got, let's just start with one and just say, okay, well, sine of x is equal to c. Now we already know that that means that the principal root is the inverse, x equals the inverse sine of c. And the alternate root is the supplement to that angle. But we haven't included this part because on the left, we have this equivalence, which says that sine of x is actually equal to x plus 2 pi times some integer n. And so what we're doing when we're trying to find all solutions is that we're in essence taking the inverse sine of both sides of this equation to find the principal root and all of its coterminal angles. And then we take the alternate root and find all of its coterminal angles as well. So the solution looks like this: x plus 2 pi times n is equal to the inverse sine of c. And thus, x is equal to inverse sine of c. And since, honestly, the plus or minus doesn't matter because this is any integer, usually the way you see it is with plus 2 pi times n, where n is an integer. So this is all of the solutions that correspond to the principal root. But we similarly have x plus 2 pi times n equal to pi minus the inverse sine of c. And then when we do this same sort of business here to isolate x, we have x is equal to pi minus inverse sine of c plus 2 pi times n, where n is any integer. And again, I've been playing a little loose and fast with the plus signs in here, but the reality is this is the set of all those solutions, and it's in a nice compact form. So, for example, if c was I don't know, if c was 1/2, you would have a solution in quadrant 1, which would be what's that? That's going to be pi over 6, and then plus any coterminal angle to pi over 6. Down here, you'd have the supplement of pi over 6, which is 5 pi over 6 plus 2 pi times n. So when solving these trigonometric equations, this is the first step. And then some equations will say, or some problems will say, find all x in some range. You know, one lap around the circle. is typically what you'll see. And there is some creeping of degrees back in this section. So I just want you to note that the way that the textbook differentiates whether solutions should be in radians and whether it should be in degrees is by whether they're using Roman letters or Greek letters. Almost exclusively, if it's a degree kind of problem, you'll see it say theta as the variable. And if the intention is to get a solution in radians, then it'll be x. Although it's possible you might see some other sort of variations. So let's try to apply this to a problem that's a sort of a linear problem. Okay, and these are the easiest ones. We've almost done them for the most part. It's just like one more step. So let's take let's solve in a given interval. So solve all x in 0 to 2 pi. And I think these all are gradients, all the ones that I've picked out anyways. And here's the equation we're trying to solve. How about 2 sine of x equal minus 1? Now that kind of looks like that linear equation. And so you know how to solve linear equations. You get the quote variable and you isolate it. Now that's by moving terms to one side and then dividing by the leading coefficient. So this is a little bit of algebra work that leads to sine of x equal to -1/2. And we know how to solve this kind of a problem from the previous section. So x is going to be equal to the inverse sine of -1/2 plus 2 pi times n, where n is some integer. That's the principal root and all of its coterminal angles. Now we know what inverse sine of -1/2 is. This just happens to be negative pi over 6 plus 2 pi times n. Now that's the principal root. Now what about the alternate root? Well, that's going to be x equal pi minus, and I'm just going to go ahead and substitute it right here because we already have the value. It's pi minus negative pi over 6 plus any coterminal angles. Now these are all of the solutions, right? And you can write this in this weird set notation that the text uses. You can look at. I don't usually try to do a lot of problems where it's find every solution, but you know, there's occasionally times that might be necessary. But to finish this problem off, now we have to well, and this reduces down to 7 pi over 6 plus 2 pi times n. Now, so it turns out that since this problem is asking us to identify only solutions between 0 and 2 pi, we have one of them. It's right there. That's 7 pi over 6. This would be for the n equal to 0. But this one, negative pi over 6, is not in the proper interval. And so what we need to do is we need to add 2 pi to it, which will change, which will give us the sort of where n equals 1, a solution of 11 pi over 6. So the final solutions, I'm right there at the end of the page here. I'm going to go ahead and try to finish this problem. X is an element of the set that contains 7 pi over 6 and also 11 pi over 6. And so this is our final solution down here. Okay, so let me grab another sheet and do a couple more of these. We're going to start, since the techniques are always the same. I'm going to start speeding up just a little bit. So section 6.2, now on page 3. Okay, so let's try to solve this problem. How about -4 cosine of x plus equal to 2 root 3. Okay, so again, we just isolate cosine. Cosine of x is going to be equal to 2 root 3 over -4, which simplifies to negative root 3 over 2. So remember, with cosine, the principal and alternate root were simply plus or minus the inverse cosine, right? So we can go straight to the solution here. X is equal to plus or minus the inverse cosine of negative root 3 over 2. And like before, to be careful here, there should be a plus 2 pi times n, where n is any integer. Okay, so now what do we, as you recall, this value is an angle in quadrant 2, and it's where cosine is okay, so the reference angle is pi over 6, so this is actually 5 pi over 6. So we end up with plus or minus 5 pi over 6 plus 2 pi times n. And the solutions that will come out of this, because we only want this this group, or out of this very narrow range, is x is an element of the set that contains 5 pi over 6, and it's not negative 5 pi over 6, it's actually 7 pi over 6. And this is where you're using the positive branch and the negative branch with n equal to 1. Okay, let's try another one. Let's do one that has tangent in it. I've got so many of these, but they're really so relatively easy that I don't really see a whole lot of point in messing with them too much, because we'll do these same kind of techniques with other stuff. But since I haven't really talked about how tangent works with this whole business, let me be really careful, because this one's sort of one that's new and interesting. So for tangent of x equal to 4 root 3. Okay, so previously we had said, all right, you know, you can think this is also equal to something with its period. So so 4 tangent of x, I'm sorry, plus, well, so my signs don't get messed up. Let me just use a negative sign, which is what I probably should have done in the first place. X minus 2 pi times n, or sorry, it's just pi times n, because the period on tangent is just pi. So equal to 4 root 3. Now isolate this bad boy. You've got tangent of x minus pi times n equal to square root of 3. So x minus pi times n equals the inverse tangent of square root of 3. Now, here's the thing. Remember, there was an alternate root, and the alternate root was to add pi, right? I mean, it was just take you know, the value that's in the opposite quadrant. Well, now that we have a period of pi here, we don't really need that. That alternate root doesn't really help any, because we're already covering it with this periodicity term. So x becomes the inverse tangent of square root of 3 plus pi times n. And that will take care of all solutions, both the principal root and their coterminal angles, as well as the alternate root and its coterminal angles. So this becomes, let's see, that's pi over 3, I think, plus pi times n. Now to come in, for the values that are inside the appropriate range, then x will be in a member of the set that contains pi over 3 and also 4 pi over 3. Okay, so that's kind of, I think, it for linear methods. I'm going to come back and start showing things with factoring, quadratics, and I think I will get to some point where maybe I can do, I will try to focus on a couple of the factoring, and maybe some that require the use of a calculator too, because I think that's something that we've avoided. And in this section, there are certainly, calculators are certainly used for things. I've found in the past that, you know, maybe because of the way I teach the class, students become adverse to using a calculator because they figure, well, maybe that's supposed to be exact. There are certainly situations where it's appropriate, and I'll try to point some of those out. Okay, I will see you on the next video.